So we have quite a few different results to talk about today. Most are small. I won't do any long detailed proofs of them or anything. Here's the first one, just picking up from where we left off. But before we do that, I forgot that I wanted to mention something about the homework. One of the homework problems, I forget which one it is, I believe it's the second one in the list, so 1D or 1E 9 or something. It says, suppose you have an isosceles trapezoid. So trapezoid is a quadrilateral where exactly two opposite pairs, or sorry, exactly one opposite pair of sides, so two opposite sides are parallel, so these two are parallel here. That's a trapezoid. An isosceles trapezoid is when the other two sides, the other two opposite sides, are equal in length. So this is an isosceles trapezoid. And the problem that I assigned is to show that the two diagonals in an isosceles triangle, or sorry, isosceles trapezoid, are necessarily equal in length. I've thought about this quite a bit, and I don't see any way to do this without showing that these base angles here are congruent to each other. This is actually a separate problem in the book. I believe it's number 4 or number 5 from this section. And proving that these base angles are congruent to each other is a bit of a trick to it. And the trick is this. So here's A, B, C, D. The trick for showing that these are congruent is come in to point D, draw in a parallel line segment passing through D that's parallel to AB. So put this line segment in. Here's E. Okay, so this is going to be parallel to AB. What do I know then? It's parallel, and these are parallel. So ABED, that's a parallelogram, right? What's always true about sides of parallelograms, opposite sides? Equal in length, right? Don't know how much you can say about the angles, but I can always say that the opposite sides are equal in length. So this is the same length as AB, right? What else can I say about parallel lines? Well, BE is a transversal of these two parallel lines. So those two corresponding angles are congruent. Corresponding angles are congruent. This triangle right here, DEC, that's an isosceles triangle, so its base angles are congruent. And here you have the result. These two base angles are congruent to each other. And using that, you can now go on to prove the result that those diagonals are equal in length. But I don't think there's much left to do at this point, but I'll leave that to you. All right, so there's the trick. And that should be part of your proof, right? Because that's something else that you're showing. So anyway, where are we? We were talking last time, we had this main theorem, right? We had this main theorem that said, if I have a circle and I draw in an inscribed angle, so here's the inscribed angle ABC. Well, this angle ABC is equal in degrees to 1/2 of the arc that it subtends. Right? So the angle ABC is 1/2 of that arc in degrees. Where this sort of the angle measure of an arc is just the number of degrees that this encompasses from the whole circle. Or in other words, if I put it in the center, it's this angle right here. Okay, so we had this result. That's the main theorem from last time. Didn't prove it, still not going to find time to prove it today, but it's proven in the text if you want to give it a read. And we were going through several corollaries. So here's the one we have now. This corollary says if I have two secants. So what's a secant? A secant is just a line that passes through 2 points in the circle. Or another way to think of this is a secant is an extended chord. So here's a chord. I'm just going to extend it outside the circle. So here I have two secants that intersect at an exterior point. that in my notes I've called x. So here's my two secants, and I'm going to label them, here's the point A, here's the point B, here's the point C, here's D. So a secant is, again, it's just a straight line that passes through the circle at 2 points, but one way to think of it is the textbook's definition of an extended chord. So here's what we have. We have two secants, and we're looking at the angle between these two secants that starts from this point x. So we're looking at this angle AXB. And the claim here, the corollary of this big theorem, is that this angle, and last time we had a similar result for chords that intersected on the interior, now these chords sort of intersect at this exterior point, this angle is equal in degrees to half the positive difference between the two subtended arcs. So here I've got this subtended arc, CD, and this subtended arc, AB. If I'm going to take the difference, well, obviously one is longer than the other, right? One is bigger in degrees than the other, so it's always going to be half the positive difference. So I take the bigger arc minus the smaller arc. So it'll be 1/2 of CD minus AB. What was our corollary from last time? The corollary from last time was if I have two chords that intersect on the interior, right? Two chords that intersect in the interior, the angle between the chords was 1/2 of the sum of the two subtended arcs, right? Well, if they intersect in the exterior, then it's 1/2 of the difference. It's just sort of a generalization of that result. Okay, so here's what it's saying. And the proof isn't hard. I can probably fit the proof down here, if you allow me just to not write that much. And what I'm going to do is a technique very similar to last time, which is, in this picture I don't have a whole lot to work with. I want a triangle. I want to construct a triangle so that I can invoke the exterior angle theorem like last time. And in constructing this triangle, I want to have a few inscribed angles in the circle that subtend the two arcs we're looking at. So what I'm going to do is I'm going to draw on this line segment here, CB. Right, because that gives me two inscribed angles now, right? I've got this angle CBD that inscribes one of these arcs we're looking at, and it gives me this other angle ACB that inscribes, this inscribed angle that subtends the arc AB. So we have some useful angles here and a triangle where I can do some stuff with external angle theorem. So I'm just going to write down the ingredients we need. Angle ACB, this inscribed angle, that's related to this subtended arc, and that this angle is 1/2, in degree measure, is equal to 1/2 of this subtended arc AB, right? So this is 1/2 of AB. And this angle here, CBD, that's 1/2 of its subtended arc, CD. Right, so angle CBD, that's 1/2 of the subtended arc CD. And I'm going to invoke the exterior angle theorem just like we did in the last proof. So, and by the exterior angle theorem, this is the catch now, right? I know something about this angle. I'm just going to label these in the picture so you can see. I know something about this angle 1. I know something about this angle 2. And what I want to know is something about this angle 3, right? This is what we're looking for. This is what the original statement was, something about this angle here. Well, the exterior angle theorem relates to all 3 of these things, right? I know something about this, something about this. I want to know something about this. Exterior angle theorem says, well, angle 2 is actually equal to angle 1 plus angle 3. So angle CBD is equal to the sum of angle ACD, or ACB, plus angle AXB. Plus angle AXB. So I'm really kind of out of space here, but I think we can use this little bit of board left. So what does that mean? Just rearrange it. Just rearrange. That means that angle AXB, the one we're looking for, is equal to angle CBD minus angle ACB. And we already have what these are in terms of 1/2 of their subtended arcs. So that means angle AXB is, and I'm just going to factor out the 1/2 for both of them. That's 1/2 arc AB minus arc CD. Done. Any questions?
Yeah, you started with CD minus AB, and then AB minus CD. Which one is it?
Wait, which, did I get the wrong way around? Say this again?
The first time you have CD minus AB.
Oh yeah, what the hell we do
I
wrong?
think it's just the last step, the very last writing of it.
CBD, oh yeah, I went the wrong way around here. CBD was CD, thank you. CD minus AB. So these are corollaries, but they're actually extensions of the main theorem, right? The main theorem says, basically, if I have 2 chords that intersect right there on the boundary, right? If I have 2 chords that intersect right there on the boundary, then this angle is 1/2 of that arc, which is true regardless of which theorem you look at, right? If you look at this one, if you generalize this one, or if you take this special case of this one rather, where this intersection point X is right here on the boundary, well, it would be 1/2 of the big arc minus a little small arc there. But that arc has 0 length. So it's just, this angle is 1/2 of this subtended arc. And similarly, if you use the other corollary, which tells you about chords that intersect on the interior, well, it's the same thing, right? This intersects on the interior, it's 1/2 of the sum of this arc plus this arc that has 0 length. So the main theorem is sort of just this special case of either of them. So get used to this trick dealing with these things. Quite often you have to draw in extra segments to create triangles on the interior. In particular, creating inscribed angles that subtend to the arcs you're looking at. But we'll move off in a slightly different direction here. Here's a small theorem which says that the angle between a chord and the tangent at one of its endpoints is equal in degrees, equal in degrees to half subtended arc. Angle between a chord and the tangent at one of its endpoints. So here I'm just going to draw a chord, AB. Here's my chord AB. And I'm going to put in a tangent. Again, I haven't really defined tangent, but we'll do that now. What's a tangent to a circle? Give me a definition.
A line that touches a circle at only one point.
At one point, right? So there is a unique line that does that. It's a fact that it's always perpendicular to a radius passing through that point and the center. So I'll draw in. This isn't very circular, so my picture might be a little bit strange, but I'll draw in a tangent here. So here's my tangent. And I'll call it just a line segment from X to Y. And the claim, what we're claiming here, is that this angle ABY is equal to 1/2 of its subtended arc. So we sort of always talked about subtended arcs in terms of inscribed angles. Here, the subtended arc between a chord and this tangent would just be this arc AB. And so subtended arcs are always sort of the angle, or sort of the arc that's inside of the angle. And so this is equal in degrees to 1/2 AB. This is what this theorem is getting at. So yeah, tangent definition, tangent at a point. Let's redefine this actually. Tangent is a line that intersects the circle in exactly one point. If you cut through 2 points, now you're a secant. So exactly 1 point. Again, proof is not long at all, especially if we don't write a whole lot of words and we just write the implications like I'm about to. So what do we know? Well, here's what I'm going to do. I'm going to put in the diameter that passes through B. So put in a diameter to this circle. So this passes through the center, and the opposite side of this diameter, I'll call it C. All right, so let CB be a diameter. Then, angle ABY, the one we're looking for, what you'll have to believe here is, I'm not going to prove this, but that's always a right angle. And it's not hard to convince yourself of this, but that's always a right angle. So angle ABY, the one we're looking for, is 90 degrees minus this angle here, ABC. Right? Because ABC and ABY are complementary angles. Angle ABY is 90 degrees minus angle ABC. But what's angle ABC? Well, angle ABC is this inscribed angle that subtends the arc AC. So angle ABC should be 1/2 of AC. In fact, since I'm going to invoke angle measure of arcs, I should really put equal in degrees there. 90 degrees minus 1/2 of the arc AC. And I think we're done in 2 equalities now. One more. Let's factor out 1/2 from this expression. So this would be 1/2 times 180 minus AC. What's 180 degrees minus AC? Well, this is 180 degrees, right? Subtract off AC, what do you have left? You have AB. So this is 1/2. Don't need brackets anymore. In fact, again, I should have equal in degrees, 1/2 of the arc AB. Which is exactly what we wanted. So, again, I leave it to you to convince yourself that this always happens, right? If I have a tangent and a diameter meeting at the same point, then they must always be perpendicular to each other. Lots of ways you can show that. So like I said, we'll keep moving on. We've got sort of a bunch of disjointed results today. Including, hopefully we have time for it, Pythagorean theorem. So, 2 circles are said to be mutually tangent. So 2 circles are mutually tangent if they sort of share the same tangent line. An easier way to write that, though, an easier way to think about it, is 2 circles are mutually tangent if they meet at exactly 1 point. So if they intersect at exactly 1 point P. Alright, so there's P. So those are 2 mutually tangent circles. They intersect at exactly 1 point, and again, the name mutually tangent comes from the idea that there's exactly, or they share the same tangent line. So we have the same tangent line at P. Is this the only way this can occur? If you sort of think about all mutually tangent circles, would the picture always look like this? How else do they look, James?
Or one circle could be inside the other.
Yeah, so this is called externally mutually tangent. Externally mutually tangent. But you could have this case, you could have a circle that meets this circle and another one sort of inside of it that meets that circle. These are really not circular. Again, sharing the same, just only meet that point, sharing the same tangent line. So this would be internally mutually tangent. when you're working with circles, it tends to be, depending on what you're doing, in this case, the external case, it tends to be much easier. Dealing with internally mutually tangent things, you have to deal with lots of weird cases sometimes. So usually when people think of mutually tangent circles, you're thinking of this picture, unless you explicitly say, yeah, this is allowed as well. But anyway, I want a theorem about externally mutually tangent circles. Well, we could list it as a theorem, I suppose. The textbook just calls it an exercise or a problem, so we'll do that. But technically, we're proving a theorem. So it's an exercise. And the exercise is the following. Given two mutually tangent, or externally, I've left a word off here. Given two externally mutually tangent circles with a common point P, let AD and BC be two common secants. Passing through the point P, and I don't want to describe exactly how this works, so I'm just going to say as shown and then show you a picture of exactly what we have going on here. So passing through P as shown. So I'll draw a picture in a second. Show that AB and CD are parallel. Okay, so here's the picture. One circle, let's go a little bit bigger. One circle and another circle. We've got this common point P. We've got So we've got two common secants. So this will just be a chord that's extended through both of them. So here's one of these common secants. And another secant that passes through P. So how about this one? So here's our points. A, B, C, D. And in our proof, we're going to invoke the tangent that passes through P. So let's draw this tangent and label some of these points, X and Y. So tangent is this line XY. All right, so here's the situation. What we're trying to do is prove this. We're trying to show that CD is parallel to AB. In my picture, they don't look parallel at all. Why not? Because I can't draw and these aren't actually circular. But if they were perfect circles, they would be parallel. All right, so we're going to prove that. How are we going to do this? Well, here's what we're going to do. If I want to show they're parallel, one thing I can do is show that if I have a transversal passing through them, that alternate interior angles are congruent, right? So what we're going to do is we're going to show that angle C and angle B are congruent. Because CB is a transversal passing through AB, CD. So CB is a transversal through AB and CD. So to show that AB is parallel to CD, again, just using some shorthand notation here, to show that AB is parallel to CUD, it is enough to show that angle C is equal to angle B in degrees. How are we going to do that? Well, I've already drawn in this common tangent, but that's sort of x and y never appeared anywhere in the statement. So let's write down what x and y actually are. So let xy be the common tangent through the point P. Through the point P. What do we have? I want to invoke some stuff about inscribed angles and arc measures. Well, let's go to angle C here. Right, this is an inscribed angle, and it subtends as arc dp. Right, so by the main theorem, we haven't given this theorem a name, but clearly it's by the main theorem of the whole section, angle C is equal in degrees to 1/2 of its subtended arc dp. And not from the main theorem this time, but dpy. Angle dpy. What's angle dpy equal to? Well, what do we have here? We have a chord, right? We have a chord, we have a tangent, and we just showed in our very last theorem, so let me write exactly where this is coming from, and by previous theorem, angle dpy is equal in degrees to 1/2 of its subtended arc. So this would be also 1/2 of angle dp, or sorry, arc dp. So what does that mean? That means these two angles are equal to each other, right? Angle C and angle dpy are the same, because they're both 1/2 of dp. So this means angle C is equal to angle dpy. I haven't shown this yet, that's what I want to show. Well, what you can do now is repeat the argument. So I'll just, I won't repeat the argument, write down all the details, I'll just say similarly. But I promise you can repeat this argument on the other side with angle B and angle APX. So similarly, angle B is equal to angle APX. So the last observation is, how do these relate? How does APX relate to DPY?
Or vertical angles.
Vertical angles, so these angles must be the same. So finally, we have angle APX is equal to angle DPY because they are vertical. angles. So the result follows. Angle C is equal to angle DPY, angle DPY is equal to angle APX, and angle APX is equal to angle B. So just string the equalities together. So angle B is equal to angle C. Done. Which feels at a glance, I think it feels like a bit of a hard proof, but I promise the more you work with circles, the more you get used to thinking of inscribed angles and their related subtended arcs and all of the sort of corollaries that we have, you realize you have quite a few tools in there, so there's always quite a bit you can do. We have just over 10 minutes. So we'll talk a little bit about Pythagorean theorem. So this is theorem, and it's Pythagoras. And I won't write down all the details because if you know anything about math at all, you know the Pythagorean theorem says if I have a right angled triangle, side lengths ABC, then A squared plus B squared is C squared. Lots of interesting theory here, or lots of interesting history, I should say. No one really knows when this first came about, when this was first discovered, by who. There's some evidence that ancient Babylonians knew this stuff 4,000 years ago. They might have just understood Pythagorean triples, which are integer solutions to this equation and not the actual sort of geometric interpretation. Indians knew it, Chinese mathematicians knew it, or at least some version of it, but it's usually called the Pythagorean theorem because of Pythagoras. Sometimes called it's Pythagoras' theorem. I don't really like calling it Pythagoras' theorem because there's no evidence he actually discovered it. It was absolutely known to the Pythagoreans, which is sort of his community. I shouldn't say community, he was a straight up cult. This community that he formed of, there are a bunch of really good mathematicians, and it was known at least to the earliest mathematicians in the Pythagorean community. So it's often attributed to them, but no evidence that they actually originally discovered this stuff. And no evidence that Pythagoras himself discovered this theorem, or that he was a creator of mathematics at all. And one of the interesting things about the Pythagorean theorem is it probably has more proofs out there of it than any other theorem in all of mathematics. So, we will go with a proof that might well have been known to Pythagoras himself, although no exact evidence of this, and it's usually called rearrangement. And I'm not going to write down all the details, I'm just going to draw two pictures. So, here's the famous rearrangement proof. I'm going to take this, this triangle that I've drawn up here. So, side lengths. Can I relabel this? Can I call A the shorter leg that I've drawn in this picture? ABC. A, B, C. I'm going to draw a congruent copy of this triangle. I'm going to flip it over and draw it here. Does that look congruent? Well, it might be a little bit long on one side. But I'm going to draw a congruent copy here. Here's ABC. Here's another congruent copy. A, B, C. And here's one more congruent copy. A, B, C. All right, so I've just taken these four triangles, four congruent triangles. I've arranged them in such a way that I get this square in the middle with side length C. Why is it called rearrangement? Well, because I'm going to rearrange this picture. I'm going to rearrange my 4 triangles. So here's another way I can draw this exact same picture. Okay, here's triangle side A, B, C, A, B, C. So now I've taken those 2 triangles and I've stacked them on the bottom there, sort of hypotenuse to hypotenuse. And I'll do the exact same thing with this rectangle. That's formed from 2 of these guys, A, B, C, A, B, C. So obviously, the area of these 2 big squares is the same, right? Area of the big square is equal to the area of the big square. Technically, there's some stuff you should prove here. You should prove the fact that this is actually a rhombus, so it's 4 right angles and so on, so you actually have squares. But it's not too hard to do under angle consideration, since I know that all of these are right angle triangles. We won't go through all the details, but here's the 2 pictures. So the area of this big square is A plus B times A plus B. Area of this big square is A plus B times A plus B. So they're both equal to each other. Well, what's the area of the guy on the left? It would be the area of this smaller square, so C times C, C squared, plus the area of 4 triangles, right? So this would be C squared plus the area of the 4 triangles. So this is C squared. What's the area on the right? Well, it would be A squared plus B squared, there are those 2 smaller squares, plus area of the 4 triangles. A squared plus B squared plus 4 triangles. So just get rid of all 4 triangles in both pictures, and you have the result. C squared is A squared plus B squared. And it's always sort of fun to come up with a new proof of Pythagorean theorem. There's hundreds of them out there, but this is one of them that's really, really well known. It's just this rearrangement result that, again, was probably known to Pythagoras himself. Does that make sense? And again, there's details that you really should flesh out, the fact that those are right angles and so on, but it's not too hard to do. Yeah, I suppose I could argue this right now. This angle here and this angle here, well, those are the 2 angles of a single triangle, so they're complementary, right? So these 2 angles add up to 90 degrees, but all 3 of these angles are supplementary, so if these 2 are 90, then that one must be 90, right? Simple arguments like that will fill in all the details. We have 3 minutes. There's one more thing I want to say, a very quick statement, but I won't push all up here. We'll stop.